Hello everyone. The purpose of this video is to take an exercise on arrays and plotting in MATLAB, and the exercise will be drawn from the area of material science and engineering. So let's read the exercise together. The exercise has many requirements, but we'll start with reading the header of the exercise. It says there is a specimen of magnesium metal having a rectangular cross-section of dimensions 3.2 millimeters times 19.1 millimeters and is deformed in tension. So let's try to imagine how this specimen looks like. So let's try to draw this here. So it's something with a rectangular cross section, something like this. And apparently this dimension is 3.2 millimeters. This dimension is, of course, this is not drawn to scale, is 19.1 millimeters, and it's subject to tension. So there is a tensile force on it. Using the load elongation data shown in the next figure, the figure is taken from the text of Callister, Material Science and Engineering, 8th edition. Write a MATLAB script that performs the following calculations. So let's have a look at the data. Apparently, I have the load, the force F, that's applied to this specimen in different types of units, libra and Newton, and the length also in different types of units, inch and millimeters. So you likely use the millimeters units. So after this, we are asked, apparently the sample fractures at a force of 12,500 newtons. We are asked to calculate the stress and the corresponding strain. We are also given an equation to calculate the stress in terms of the force and the cross-sectional area. We also have an equation to calculate the strain epsilon in terms of the length of the sample, the current length and the original length, and there are other requirements as well. But let's get started. So we will certainly need the load length data, and we need to choose a unit system. Apparently, we'll try to get as close as possible to the SI units, so we will be using the newtons and the length. So let's actually get a new script for that purpose. Let's save it with the name mg stress strain. All right. So we will enter the force data from, of course, we will do this manually now as an array. We will learn at a later part of the course how to read the text file or an Excel sheet, but at this stage we will enter it manually. So 1380, 2780, 56, 33, 30, 7430, 8140, 9870, 12, 850, and then 1400. Still we have a couple of forces, 14340, 13830, 12500. So these are the forces in units of Newton. I can also write a comment here that this is the force in Newton. Similarly, I will create an array for the length, length in millimeter. I will call it array capital L. So the array capital L, I will use it in millimeters and then I will convert it into meters using array operations, 63.5, 63.53, 63.56, and then 63.62, 63.70, 63.75, and then 64.14, 64.41, 64. Of course, this is prone to mistakes, so it's better to learn at a later part how to enter these arrays by reading a text file. So we have 14 and 41, and then we have we made a mistake already here. So this is 65.41, and then there is 66.68, 67.95, and then 69.22, and then 70.49. So this is the array L. Just as a sanity check, let me run this and let me calculate the length of the array F to see how many elements. So there are 12 elements. Similarly, the length of the array L, also 12 elements. So at least the number of elements is consistent. So we didn't do a mistake, at least in the number of elements. So now we have the length data. I can actually convert the length right away. So let me write a comment here. Convert length to meter. I can do this right now. So the new L is the old L times, I will convert this to meter. Maybe I can divide by 1,000. So now this is in SI units. And now let's see what's required. We need to calculate the stress. Of course, I have an array for the force. And the stress is defined as the current force divided by the area. But which area here? This is the cross-sectional area at the beginning of the experiment. So that's basically the 19.1 millimeters times the 3.2 millimeters. Again, we should convert this into SI units. So let me calculate the cross-sectional area. And please, we shouldn't use a calculator here. We should rely on programming completely. And maybe I should say that this is the beginning experiment, because the area, of course, changes as the experiments proceed. But if you study material science, we will learn that this is something called the engineering stress, which is referenced with respect to the area at the beginning of the experiment. So A equals 19.1 millimeter times 3.2 millimeter. And maybe I can do the conversion right away into meters. So that will take care of converting both these numbers into meters. So this is the area. I can write a comment here in meter square. All right, I have the area. Now I can calculate the stress as an array. Because I have each one of these forces, I just need to divide each one of them by the area. So there will be an array of stresses. So here we compute the stress. Let me define a new array called stress. It is the force divided by the area, as simple as this. So remember, this is an array operation where I have the whole array is divided by a scalar, and the scalar in this case is the original cross-sectional area at the beginning of the experiment. I also need to calculate the strain, or the so-called engineering strain. So it is the current length minus the original length divided by the original length, and you also have the option to multiply this by 100 to represent it as a percentage. But what is the original length? Well, it is the length at the very beginning of the experiment, which is 63.5 millimeters. So maybe I can do something interesting here. I can define L note. Someone might say, well, why don't you write it this way? 63.5, and of course, because I converted into meters, I divide by 1,000. That's totally fine. But I would rather invoke what we learned about arrays, and especially this will be useful when we try to develop a general software that works with any alloy. Instead of typing this number again, I can actually call it L of 1, where L of 1 is the first element in the array L, which is the length array here. That's actually the 63.5 divided by 1000. Okay, so that will make our code general. In other words, if I give you the data for another specimen, the code will work, provided, of course, that I give you the correct area as well. All right. So that defines L node. Now I can define an array that's called strain. It's basically just as this equation states. It's L minus L node divided by L node. So let's actually do this. L minus L node divided by L node. And one might wonder, do I need a dot here because of array operations? Think about this for a second. In fact, we do not, because we are dividing by L node, and L node here is a scalar. So that's the strain calculation. So maybe I can combine these two lines together and write compute the strain. So now we have the stress and we have the strain. The second requirement, it says plot the stress in units of megapascal, where 1 megapascal is 10 to the power 6 times Pascal, as a function of the strain. And I'm required to do other stuff, but let's actually get to the first part here, which is the plotting. Well, first let's ask ourselves, what are the units of the stress? At this stage, and since the force is in newtons and the area is in meter square, then it's actually in Pascal. So I should say here this is in Pascal because it's the SI unit for the stress. If I want to convert this to megapascal, maybe I should write a comment here, convert into megapascal, then the new stress is the old stress. Remember, 1 megapascal is 10 to the power 6 Pascal, so it's really going to be divided by 1e to the power 6, or alternatively times 1e negative 6. It's exactly the same. It will do the same job. Now I have the stress in the units I want. The strain is unitless. I have the leisure actually to convert it into percentage, or I could leave it as is. And now let me do the plotting. So plotting, it's simply plotting the two arrays. And if you remember the study of from your studies of materials, if you took a course on material science, you will remember that the stress is typically presented on the y-axis, the strain is typically presented on the x-axis, and you would imagine that the result is a curve like this, where you start with a linear regime, usually known as the elastic regime. You enter a plastic regime, and eventually your sample breaks or fractures at some point. So let's use the plot command for the two arrays that we have. On the x-axis, we will put the strain, so strain. On the y-axis, it's the stress. So this is the plotting. We want to plot strain and stress. Let's save this. Maybe it's a good thing to test the code at this stage before we proceed, just to make sure that we didn't make any mistake. So let's run. It should generate a graph. Let's dock. I think we made a mistake somewhere here. The graph doesn't look very smooth. There is some kink here. In the last few points, I think we made the mistake in writing the data. We will have a look at this later after we continue this part. But this is the shape that you would expect, that this is the stress and this is the strain. I believe there should be a tiny mistake here because of an input of the numbers. Let's actually continue this question. It says the data should appear as red squares connected by a solid line. So remember, we can control this easily here if I make a comma and then I request the red squares and connect it with a solid line. Also, we need to make sure to label the axes. So I can put an X label here. This is a strain unitless. Clarify the units. So let's see, Y label. Stress in megapascal. Close this and insert the title. So maybe for the title, I can say that this is stress strain response of an Mg sample, a magnesium sample. All right. So let's save again, run, and make sure that we get the figure that we are interested in. Let me dock to make sure that you can see this. So everything is plotted nicely. I think we have a mistake in one of these last 3 points. Let's actually quickly have a look at them just before we proceed. In the last 3 points, did we really make a mistake somewhere here? 1383, 434, 1400, 14340, 13830, 12. I don't think we made a mistake here. Maybe in the straight, maybe 7049. Yeah, we made a mistake here. Yes, this point is not correct. It is 69 here. It's 68. So let's correct this. The other strain is fine, the other strain is fine. I think now the graph will look smoother. So sometimes you detect mistakes by eye. So now the graph looks smoother as you would expect for a typical experimental stress strain tensile test of a sample, of a metallic sample. All right, so we are done with the first 2 parts of the question. Let's see what else do we have here. We are asked to the point where the graph changes from a straight line to a curve is known as the yield point. Before this point, the material is in the elastic regime, and after it, the material is in the plastic regime. Use a textbooks to mark the yield point and save the plot. So let's see, just to recap what is stated in this question. We can actually move down here. So it's what we said at some point earlier, that a typical stress strain behavior under tensile test looks like this. So there is an elastic regime, and then and it's usually linear, and then after that there is a plastic regime. Let's denote this with another color. And eventually the sample breaks at the end. So at the end of the experiment, it breaks. So the last point in the elastic regime is known as the yield. So the stress at this point is known as the yield stress. It's not the maximum. So the maximum is usually in the plastic regime, but it is before the maximum. This is called the yield point. The corresponding stress is called the yield stress. It's an important point because it marks the end of the elastic regime. So let's actually try to mark it using a box. Of course, it asks us to save this plot for a later inspection. So let's run, dock the figure. If you look here in the figure tools, you can actually insert from the insert menu here. You can insert the textbooks, and I can with visual inspection of the graph, I can safely say that this is a linear part tentatively, and I think this point marks the end of the linear regime. Again, this is up to visual inspection. You might want to make this in actual study of materials. You might want this to be more specifically defined. So I would say here that this is the yield point. And that's it. I have my box pointing to the place of the yield point, and I can save this graph maybe from here, save it as either as a MATLAB figure or even as a PDF or an image. It's totally up to me. So I'm going to save this as an MG alloy Let me save, and I can later on inspect the picture itself rather than the graph. There is one last thing required, so let me close the figure now, is to calculate Young's modulus using a point in the linear regime. Of course, when it says using a point, this is under the assumption that you will use the origin as the other point. Because let's get back to the basics. What's the definition of Young's modulus? Young's modulus is defined as the slope of this linear regime, and it has the same units as the units of the stress. So typically people take one point, which is the origin, and if this is really a straight line, all what you need is some other point somewhere here, maybe this point or this point or this point, just any other point on the graph. All right. Of course, there is a more sophisticated way to calculate Young's modulus using least square regression, but this is we will leave to another time later in the course. We can or in another course when we study numerical methods, we will examine the concept of regression. But at this stage, we will do something very simple. We will take the origin as one point, and just any other point on the curve, maybe either the second point or the third point. Let's actually take the third point. So I'll take the origin and the third point, and I will use this to calculate the slope, which is Young's modulus. So let's do this here. Compute y, or Young's modulus. So I will say y equals the numerator is two stresses. Remember, I can type. I can use the arrays because there is an array that contains the stresses, and all what I need is to pick the first element and the third element of the array. So remember, the array is called stress. So stress of 3 minus a stress of 1. This will be my numerator for the slope calculation. Remember, let's go again to the basics. Slope of a straight line is delta y over delta x, the change in the y over the change in the x, the change in the y over the change in the x. So that's the numerator divided by the denominator, which is going to be strain of 3 again, minus strain of 1. I have to put these parentheses. Remember, there are parentheses for indicating the element of the array, and just the global parentheses on the denominator and the numerator. And let's remember that this is in units of megapascal. All right, I can put the semicolon here, and to show this to the reader, maybe I can use this command, the display command, and I can write a text here that Young's modulus. Young's is one annoying word because it has an apostrophe s, and we didn't discuss how to deal with this. So let's call it this way. The modulus of elasticity, Young's modulus, is, and let's close this, leave a space here. I need num to str to convert a number into a string, and third, I will write the units here in megapascal. All right, so I think I need also square brackets for indicating an array, right? Remember, in this you can display an array of strings as we are doing here, and the first string is the sentence. The second is by converting y into string or using the numerical to string function, and then the megapascal is the last string. Let's run this one more time. Of course, it shows the figure, but it also calculated the Young's modulus in megapascal. And it's quite a large number, I would say. it's 48,000, and Young's modulus is typically reported in giga. So let's do one more edit, and that we will end the exercise. I will convert Young's modulus, convert y into gigapascal. So the new y is the old y divided by 1,000, and here I will correct this and I will say gigapascal. Let's save. Let me clear the window here. Let me run one more time. Again, I can dock the figure. The figure always is generated, but it says this time that the modulus of elasticity is 48.1375 gigapascal. And that's a typical number for Young's modulus for metals. Let's conclude this video by saying that with a combination of arrays and plotting, we managed to do an exercise from the area of material science. We can do similar exercises from other areas of engineering, and this, I hope, shows the power of coding and plotting, of course, that can help in solving engineering problems. Thank you so much, and see you in another video.